A computer chip failed 15 billion miles from Earth. The engineers who built it are retired or dead. The documentation exists only on yellowed paper and fading mimeographs. And every command you send takes 45 hours to get a response. This is the story of how NASA saved Voyager 1. On November 14, 2023, humanity's most distant ambassador went silent. Not completely silent. Voyager 1 was still out there, still receiving commands, still functioning. But when it tried to speak back, all that came through was gibberish. A repeating pattern of ones and zeros that meant absolutely nothing. For 5 months, a dozen engineers at NASA's Jet Propulsion Laboratory worked to diagnose a problem they couldn't see, on hardware they couldn't touch, using technology older than most of their colleagues. The spacecraft was so far away that light itself, the fastest thing in the universe, took nearly a full day to reach it. What they accomplished represents one of the most extraordinary remote repairs ever attempted. But to understand why this matters, you need to understand what Voyager 1 actually is. In 1977, a rare planetary alignment occurred, something that happens once every 175 years. The outer planets of our solar system lined up in such a way that a spacecraft could visit multiple worlds using gravity assists, slingshotting from one planet to the next. Without this alignment, a trip to Neptune would take 30 years. With it, 12. NASA built 2 spacecraft to take advantage of this cosmic opportunity. Voyager 1 and Voyager 2 launched that summer, carrying instruments to study Jupiter, Saturn, and their moons. The mission was designed to last 5 years. The spacecraft were built accordingly, robust enough to survive the journey, but not necessarily engineered for decades of operation. They exceeded every expectation. Voyager 1's journey through the solar system revealed worlds we'd only glimpsed through telescopes. At Jupiter, it discovered active volcanoes on Io, the first time volcanic activity had been observed anywhere beyond Earth. 9 volcanoes erupting into space, driven by tidal forces from Jupiter's immense gravity. 4 months later, Voyager 2 passed by and found 8 of those 9 volcanoes still active. At Saturn, Voyager 1 revealed the intricate structure of the planet's rings, discovered new moons, and provided the first detailed images of Titan's atmosphere. Then it did something remarkable. Instead of continuing to Uranus and Neptune like its twin, Voyager 1 used Saturn's gravity to fling itself upward, out of the plane of the solar system, heading toward interstellar space. By 2012, Voyager 1 had traveled so far that it crossed the heliopause, the boundary where the sun's influence ends and interstellar space begins. It became the first human-made object to leave the solar system. And it kept going. The spacecraft itself is deceptively simple. 3 computers, built in the 1970s, with a combined memory of 68 kilobytes. Your smartphone has millions of times more computing power. The button you press to unlock your car door has more processing capability than Voyager's entire system. But here's what makes those computers remarkable. They've been running continuously for nearly 50 years. Through temperature extremes, cosmic radiation, and the vacuum of space. They've processed data from planetary flybys, managed course corrections, and maintained communication with Earth across distances that make the mind real. Until November 2023, when one of them broke. The Flight Data Subsystem, the FDS, is responsible for collecting information from all of Voyager's scientific instruments and engineering sensors, organizing it into a coherent format and preparing it for transmission back to Earth. It's the spacecraft's voice, essentially. The system that takes raw measurements and turns them into data we can understand. When it failed, Voyager 1 didn't go completely dark. It could still hear us. Commands sent from Earth were received and executed normally. But when the spacecraft tried to respond, when it tried to send back the data it was collecting, all that came through was noise. NASA described it as a repeating pattern of ones and zeros. The spacecraft was stuck in a loop, sending the same meaningless sequence over and over. It was like talking to someone who could understand everything you said, but could only respond with the same nonsensical phrase. The engineering team knew they had to diagnose the problem. But the challenge they faced was unlike anything in typical computer repair. You can't reboot Voyager 1. You can't plug in a monitor and see what's happening. You can't swap out components or run diagnostic tools directly. And then there's the distance. Voyager 1 is currently over 15 billion miles from Earth. Light, traveling at 186,000 miles per second, takes 22.5 hours to reach the spacecraft. Another 22.5 hours for the response to come back. Every single interaction with Voyager requires a minimum of 45 hours. Imagine debugging code with a 45-hour delay between each command and its result. You can't iterate quickly. You can't try something, see it fail, and immediately try something else. Every attempt requires careful planning, thorough review, and 2 full days of waiting. Make a mistake, and you might make things worse, or you might permanently disable the spacecraft. The team started with what they knew. Voyager has 3 computers, the FDS, the Command Control System, and the Attitude and Articulation Control System. The Command Control System was clearly working. It was receiving and executing commands. The AACS was also functioning. The spacecraft maintained its orientation, keeping its antenna pointed at Earth. So the problem had to be in the FDS. But what specifically had failed? For months, the engineers sent commands, trying to coax any kind of meaningful response from the spacecraft. They reviewed decades-old documentation, trying to understand how the original designers had structured the system. Many of those designers were retired. Some had passed away. The team was essentially doing archaeology, piecing together the thinking of engineers from nearly half a century ago. Then, in early March 2024, they tried something different. They sent what they called a poke command, essentially asking the FDS to try running different sequences within its software. The hope was that the spacecraft might be able to work around whatever was broken and resume normal operations. On March 3rd, something changed. The signal coming back from Voyager 1 looked different. There was activity from one section of the FDS that stood out from the rest of the garbled data. It still wasn't in the normal format, but it was something new. An engineer with NASA's Deep Space Network, the global system of massive radio antennas that communicate with distant spacecraft, was able to decode it. What they found was extraordinary, a complete readout of the FDS memory. It was like a patient who couldn't speak suddenly handing you their complete medical record. The team compared this memory dump to documentation of how the FDS should normally function. And there, buried in the data, they found the problem. 3% of the FDS memory was corrupted. 3% doesn't sound like much, but in a computer with only 68 kilobytes of total memory, 3% corruption was enough to completely disable the system. And the team could see exactly which memory chip had failed. A single chip, responsible for storing a portion of the FDS memory, including some of the computer's software code, wasn't working. After 46 years of continuous operation, after countless thermal cycles, after exposure to radiation in interstellar space, one component had finally given up. The question was, could they work around it? You can't replace a chip on Voyager 1. You can't send up a repair mission. The spacecraft is in interstellar space, traveling at 38,000 miles per hour, getting farther from Earth every second. Whatever solution the engineers devised had to work with the hardware exactly as it existed, 15 billion miles away. The team came up with a plan that was elegant in concept, but staggeringly complex in execution. They would move the affected code to a different location in the FDS memory. The problem was that no single location had enough space to hold all of it. The code would have to be divided into sections and stored in multiple places. But it wasn't as simple as just copying and pasting files. Each section of code had to be modified to work in its new location. Every reference to the code's original location throughout the entire FDS memory had to be updated. The sections all had to function together as a cohesive whole, even though they were now scattered across different parts of the computer's memory. And they had to do all of this with 68 kilobytes of total memory, 3% of which was now completely unusable. The engineers started making difficult choices. They identified code that was no longer needed, routines designed for high data rates during planetary flybys, which were irrelevant now that Voyager was in the sparse environment of interstellar space. Code used to process data from Jupiter, functions that hadn't been used in decades. They deleted what they could. They reorganized what remained, and they carefully, methodically prepared the modified code for transmission to Voyager 1. The first phase focused on the code responsible for packaging engineering data, information about the spacecraft's health and status. This was strategic. If the repair worked, engineers would immediately be able to see how Voyager was doing, which systems were functioning properly, whether there were other problems lurking. If it failed, they could try again without losing the ability to receive scientific data. On April 18, 2024, they transmitted the command. Then, they waited. 45 hours, almost 2 full days. The signal crawling across 15 billion miles of empty space at the speed of light. On April 20th, the response came back. It worked. For the first time in 5 months, Voyager 1 was sending coherent engineering data. The repair had succeeded. After months of troubleshooting, after poring over yellow documentation, after carefully crafting each command, the team had done it. They had fixed a computer from 15 billion miles away. But the work wasn't finished. The engineering data was flowing, but the scientific instruments were still silent. Those instruments, studying plasma waves, magnetic fields, cosmic rays, particles in interstellar space, represented the entire reason Voyager 1 was still operating. Getting them back online would require relocating more sections of code. The team continued their work. On May 19th, they transmitted the commands to restore scientific operations, and one by one, the instruments came back online. By June 2024, All 4 scientific instruments were back online and transmitting data. But this wasn't just about getting sensors working again. These instruments were measuring things no human-made object had ever measured before. Plasma waves rippling through interstellar space. Magnetic fields from sources we barely understand. Cosmic rays that have traveled millions of years through the galaxy. Every data point was unique, irreplaceable. And here's what makes this even more remarkable. Those instruments weren't designed to work in interstellar space. They were built to study Jupiter and Saturn during flybys that were supposed to last a few months. The designers never imagined they'd still be operating 47 years later in an environment they'd never tested for. The repair revealed something profound about engineering. You can build something incredibly robust without knowing exactly what challenges it'll face. The Voyager team in the 70s built redundancy into systems they didn't fully need. They added backup modes for failures they couldn't predict. They created fault protection routines for scenarios they couldn't imagine. And decades later, those decisions saved the mission. But let's talk about what this repair actually means for how long Voyager can keep going. Because that's the question everyone wants answered. How much longer until we lose contact forever? The honest answer is complicated. Voyager's death won't be sudden. It'll be gradual, system by system, instrument by instrument. Power is the limiting factor. Voyager's electricity comes from radioisotope thermoelectric generators, essentially nuclear batteries that convert heat from decaying plutonium into electrical current. When Voyager launched, those generators produced about 470 watts. Nearly 50 years later, that's dropped to around 220 watts. And it keeps dropping, about 4 watts per year. Every year, the engineers have to make choices about what to turn off. They've already shut down heaters for most of the scientific instruments. Those instruments were tested to specific temperature ranges before launch, and they're now operating well below those limits. The fact that they still work is surprising, but eventually something will get too cold and stop functioning. They've turned off backup systems, redundant computers, safety features, anything non-essential. They're running on the absolute minimum power configuration needed to maintain contact with Earth and collect science data. Current projections suggest that by the early 2030s, there won't be enough power to run even a single scientific instrument. Maybe 2031, maybe 2036. The uncertainty comes from not knowing exactly how the power will decline and which systems will fail first. But here's where it gets interesting. Even after the science instruments shut down, Voyager might still be able to send engineering data, temperature readings, power levels, attitude information. That data would tell us about the spacecraft's health and about conditions in interstellar space, even without dedicated science instruments. That could extend the mission another few years, maybe until 2036 or 2037. And then Voyager will finally go silent. Not because it stops working, but because it won't have enough power to run its transmitter. The spacecraft will continue flying through space, still executing its onboard programming, still taking measurements that no one will ever receive. It'll become a ghost ship, a time capsule containing the golden record, that gold-plated copper disc with sounds and images from Earth, designed for any civilization that might someday find it. But before we get sentimental, there's another challenge looming: distance. Voyager is currently about 15 billion miles from Earth. By November 2026, it'll reach what's called one light day. The distance light travels in 24 hours. At that point, if engineers send a command at 8 a.m. on Monday, they'll get a response at 8 a.m. on Wednesday. Think about what that means for troubleshooting. Right now, with a 45-hour round trip, if something goes wrong, you can send a diagnostic command on Monday and get results back Wednesday morning. You can analyze that, prepare a fix, send it Wednesday afternoon, and see if it worked Friday morning. At one light day, that becomes Monday to Wednesday. Analysis Wednesday, fix sent Thursday, results Saturday. The whole process takes a week, and Voyager keeps getting farther away. The troubleshooting process keeps getting slower. Each repair attempt requires more patience, more planning, more precision. The engineers working on Voyager today are acutely aware they might be the last generation to interact with it. When Voyager finally goes silent, that silence will be permanent. There's no way to restart it, no way to send a repair mission. Once the power runs out, humanity's most distant ambassador becomes an artifact. But here's something that doesn't get talked about enough. The deep space network that listens to Voyager. That's not getting any younger either. The DSN consists of 3 antenna complexes, one in California, one in Spain, one in Australia, positioned roughly 120 degrees apart around the globe so that at least one can always see Voyager. These antennas are massive. The largest are 70 meters in diameter, about 230 feet across. They're among the most sensitive radio receivers ever built, capable of detecting signals that arrive at Earth with less power than it takes to run a digital watch. But they're also aging infrastructure that requires constant maintenance, and they're in constant demand. Dozens of missions rely on the DSN, Mars rovers, asteroid probes, the James Webb Space Telescope. They're all competing for antenna time. As Voyager gets farther away and its signal gets weaker, it needs more and more antenna time to collect the same amount of data. Eventually, the DSN might have to make hard choices about how much time to dedicate to a mission that's producing diminishing returns. That's not a criticism, it's just reality. The DSN is a limited resource, and newer missions might provide more scientific value per hour of antenna time. But there's something profoundly moving about the effort being poured into keeping Voyager alive. This isn't about maximizing return on investment. It's about not giving up on something we sent into the darkness. The engineers who fixed Voyager in 2024 weren't thinking about cost-benefit analysis. They were thinking about the fact that this spacecraft has been flying for 47 years, through conditions no one predicted, sending back data no one else can collect. They were thinking about the original team who built it in the 70s, about the scientists who studied its Jupiter and Saturn data, about the fact that Voyager is doing something unprecedented, measuring the space between the stars. And maybe they were thinking about what it means to be human, to send something into the void and keep listening for its voice decades later. Because that's what this repair really represents. It's not just about fixing a computer, it's about maintaining a connection across 15 billion miles, about refusing to let distance and time sever the link between us and something we created. The repair also revealed how much institutional knowledge is required to keep these old missions running. The engineers working on Voyager today aren't the ones who built it. They're working with documentation from the 70s, yellowed papers, old mimeographs, design notes written by people who've since retired or passed away. They're essentially archaeologists, piecing together the thinking of engineers from 50 years ago. Why did they design this system this way? What were they trying to accomplish? What assumptions did they make? It's reverse engineering decisions made before many of the current team members were born. And that knowledge is fragile. Every year, more of the original Voyager engineers retire. More institutional memory disappears. The current team is racing to document everything they learn, to preserve the knowledge for whoever comes after them. Because even though Voyager will eventually go silent, the mission isn't over. When the spacecraft finally stops transmitting, engineers will still need to understand what happened. They'll analyze the final data. They'll write reports documenting the end of the mission. They'll study what failed and why. And that knowledge will inform future missions. Every lesson learned from Voyager about radiation damage, about thermal cycling, about memory corruption, gets passed forward to the next generation of spacecraft. In that sense, Voyager's legacy extends far beyond its own operation. It's teaching us how to build things that last, how to design systems that can handle the unexpected, how to create machines that keep working decades past their intended lifespan. The October 2024 incident provided another example. Voyager's fault protection system kicked in and switched from its main X-band transmitter to the backup S-band transmitter, a radio that hadn't been used since 1981. The S-band operates at a lower frequency, which means the signal is even weaker when it reaches Earth. Finding that signal after 43 years was like trying to hear a whisper from across an ocean. But the Deep Space Network found it. They detected that impossibly faint signal and re-established contact. And then they carefully switched Voyager back to its main transmitter without causing any additional problems. That whole event demonstrated both the spacecraft's built-in resilience and the ongoing challenge of operating at such extreme distances. Voyager is still protecting itself, making autonomous decisions when communication with Earth takes too long. The spacecraft is, in some sense, taking care of itself, making choices to preserve its own survival without waiting for human input. And that autonomy becomes more important as distance increases. The farther Voyager gets, the more it needs to handle problems on its own, because the round-trip communication time keeps growing. By the time we lose contact, Voyager will be making all its decisions independently, following programming written decades ago by engineers who couldn't possibly have predicted every scenario it would face. It's a strange thought. This machine, built by humans, will eventually operate completely beyond human influence, still executing instructions, still following its mission profile, but entirely alone in the darkness between stars. The repair in 2024 might be the last major fix we're able to perform. The next time something goes wrong, we might not have enough power to implement a solution, or the problem might be in a system we can't access remotely, or we might simply run out of time as the spacecraft moves farther away. But for now, Voyager is working. All 4 science instruments are collecting data. The engineering systems are healthy. The spacecraft is flying through interstellar space, measuring conditions that nothing else can reach. And every day, that impossibly faint signal reaches Earth, carrying information from the edge of human exploration, a whisper from 15 billion miles away, transmitted by a machine that refuses to stop working. The data Voyager sends back now is different from what it transmitted during the planetary encounters. Back then, The spacecraft had power to spare and could transmit at high rates. Images of Jupiter's storms, close-ups of Saturn's rings, video sequences showing volcanic eruptions on Io. The bandwidth was enormous compared to what's available today. Now, with power supplies depleted and distance-stretching signal strength to its absolute limit, Voyager transmits at speeds measured in bits per second, not kilobits, not megabits. Individual bits trickling across 15 billion miles of empty space. A single image that took minutes to transmit in 1980 would take weeks today. So the mission has adapted. Instead of pictures, Voyager sends measurements. Readings from instruments that detect magnetic fields, plasma waves, cosmic rays. Data that can be compressed into tiny packages and transmitted slowly but continuously. The spacecraft is no longer a photographer documenting alien worlds. It's a probe sampling conditions that nothing else can reach. And those conditions are strange. Voyager crossed the heliopause in 2012, the boundary where the sun's influence ends and interstellar space begins. Before that crossing, instruments detected the solar wind, particles streaming outward from our star. After the crossing, the readings changed. Different particles, different magnetic field orientations. Evidence that Voyager had entered a region shaped by forces from outside our solar system. That transition wasn't sharp. The boundary between solar and interstellar space turned out to be more like a turbulent coastline than a clean edge. Voyager detected oscillations, variations, regions where solar particles mixed with interstellar ones. The data revealed complexity nobody had predicted. Scientists are still analyzing those measurements, still trying to understand what the readings mean. Because before Voyager, we had no direct observations of interstellar space. We had theories and models, but no actual data. Voyager provided the first ground truth, the first measurements we could compare against predictions, and the predictions weren't always correct. The magnetic field orientation in interstellar space, for example, surprised researchers. Models suggested it would point in one direction. Voyager's instruments showed it pointing differently. That discrepancy forced scientists to revise their understanding of how our solar system moves through the galaxy. The cosmic ray measurements are equally important. Inside the heliosphere, the sun's magnetic field deflects many cosmic rays, preventing them from reaching the inner solar system. Outside that protective bubble, cosmic ray intensity increases dramatically. Voyager's instruments detect particles that have traveled across the galaxy, carrying information about distant supernovae and the structure of interstellar space itself. Every bit of data matters. Engineers know this. They've spent decades optimizing how information gets packaged and transmitted, choosing which measurements to send first, which data can wait, how to compress readings without losing critical information. It's a constant balancing act between scientific value and transmission capacity. The plasma wave instrument provides some of the most intriguing data. It detects oscillations in the surrounding plasma, charged particles that fill the space between stars. These waves carry signatures of nearby objects and events. When Voyager's instruments detect certain frequencies, scientists can infer things about the density and temperature of the local environment. In 2012 and 2013, the plasma wave instrument detected something unexpected. Oscillations that suggested Voyager was passing through a region of increased plasma density. Analysis revealed these were pressure waves, disturbances propagating through interstellar space, possibly triggered by solar activity or interactions with the galactic environment. Those measurements continue. Every few months, engineers review the incoming data and adjust which instruments get priority. They balance power consumption against scientific return. Sometimes they shut down one instrument temporarily to give another more resources. It's like conducting an orchestra where half the musicians can only play for a few hours before needing rest. The magnetometer keeps running almost constantly. It draws relatively little power and provides crucial orientation information. Voyager needs to know which direction it's pointing, both for scientific measurements and for keeping its antenna aimed at Earth. The magnetometer readings help maintain that alignment. But here's something most people don't realize. Voyager is tumbling. Very slowly, but measurably. The spacecraft has thrusters that can correct this rotation, but using them consumes fuel and generates heat that affects sensitive instruments. So engineers let the tumbling continue, compensating for it in their calculations, rather than fighting it directly. This creates challenges for data transmission. As Voyager rotates, its antenna sweeps past Earth. During those sweeps, the signal strength peaks. Between sweeps, it drops. Engineers have to time their commands carefully, sending them when the spacecraft's orientation is most favorable. They track Voyager's rotation rate, predict when the antenna will point toward Earth, and schedule transmissions accordingly. The Deep Space Network handles this complexity seamlessly. Computers monitor the signal strength in real time, adjusting receiver settings to maintain lock on Voyager's transmission. When the signal fades below a certain threshold, the system switches to more sensitive detection modes. When it strengthens again, they optimize for data rate instead of sensitivity. What's remarkable is how well this system works, despite being designed in the 1970s. The fundamental architecture hasn't changed. 3 antenna complexes spaced around Earth, each site equipped with massive dishes that can track spacecraft across billions of miles. The same basic infrastructure that communicated with Voyager during its Jupiter encounter still handles its interstellar transmissions. Of course, the equipment has been upgraded. Modern receivers replaced vacuum tube technology. Digital signal processing replaced analog circuits. Computer systems that once filled entire rooms now fit in server racks. But the core concept remains identical. Sensitive receivers, massive antennas, and careful management of a resource that's always in short supply. Because here's the constraint nobody talks about. The Deep Space Network supports dozens of active missions, Mars rovers, asteroid probes, missions to Jupiter and Saturn, spacecraft studying the Sun. They're all competing for antenna time, all needing to transmit their data back to Earth. Voyager gets a few hours per day, sometimes less. The scheduling system allocates time based on mission priorities, scientific return, and operational requirements. Critical missions get more time, routine operations get less. Voyager, despite its historic significance, often finds itself waiting in queue behind missions with more immediate needs. This means engineers can't continuously monitor the spacecraft. They schedule contact windows, transmit commands during those windows, and wait for responses. Between windows, Voyager operates autonomously, following its programmed instructions, collecting data, and storing it for later transmission. The data storage capacity is minuscule by modern standards. Voyager can buffer a few hours' worth of measurements before memory fills up. If it doesn't transmit that data soon enough, New measurements overwrite old ones. Engineers have to ensure regular contact windows to download stored data before it's lost. They've gotten very good at predicting how much data will accumulate between contacts. They know which instruments generate the most information. They understand compression ratios and transmission rates. They can calculate exactly when memory will fill and schedule downloads accordingly. But unexpected events complicate these calculations. A solar outburst might trigger additional plasma wave activity, generating more data than predicted. A cosmic ray storm might increase particle counts, filling buffers faster than expected. When this happens, engineers have to scramble, requesting emergency antenna time, adjusting priorities, sometimes accepting that some data will be lost. The November 2023 failure made all of this impossible. Without readable telemetry, engineers couldn't tell what data was being collected. They couldn't determine which instruments were functioning. They couldn't even verify that commands were being executed correctly. The spacecraft became a black box, receiving instructions but providing no meaningful feedback. That's why the April repair was so critical. Restoring engineering telemetry didn't just mean seeing how the spacecraft was doing. It meant regaining the ability to manage data collection, schedule instrument operations, and optimize limited resources. Without that capability, Voyager might as well have been lost completely. The repair also revealed something about the spacecraft's architecture that most people overlook. Voyager has 3 separate computers, each handling different functions. The flight data subsystem packages science and engineering data. The command computer subsystem processes instructions from Earth. The attitude and articulation control subsystem manages orientation and pointing. These computers don't communicate directly. Instead, they share information through a data bus, a shared pathway where each computer can read messages left by the others. It's like a bulletin board where different departments post updates and requests. The system is simple, robust, and designed to keep functioning even if one computer fails. When the FDS encountered memory corruption, it couldn't package data properly. But the other computers continued operating normally. The command computer still received instructions. The AACS still maintained pointing. The spacecraft didn't crash or shut down. It just lost its ability to speak coherently. This architectural separation is what made the repair possible. Engineers could send commands to the command computer, which would pass them to the FDS, even though the FDS couldn't respond properly. They could try different diagnostic sequences, probe different memory locations, and eventually extract that crucial memory dump, all because the computers remained partially independent. Modern spacecraft often use more integrated designs where a single powerful computer handles multiple functions. That approach offers advantages: faster processing, easier software updates, more efficient resource sharing. But it also creates single points of failure. If that one computer fails, the entire spacecraft might become inoperable. Voyager's distributed architecture, primitive by today's standards, provided resilience that more advanced designs might lack. The redundancy, the separation of functions, the simple communication protocols, all of these meant that partial failures didn't cascade into total loss. Engineers designing current missions study Voyager's architecture carefully. They're learning lessons about redundancy, about simplicity, about building systems that can survive decades of operation in hostile environments. Some of those lessons are being incorporated into new spacecraft. Others are being set aside in favor of more capable but less robust designs. It's a fundamental trade-off in engineering: capability versus reliability, performance versus longevity. You can build something that does everything perfectly under ideal conditions, or you can build something that keeps working when conditions are terrible. Voyager represents the latter philosophy, and that philosophy has kept it alive for 47 years. The power situation deserves closer examination because it shapes every decision about Voyager's future. When engineers talk about managing declining power, they're not describing some abstract technical challenge. They're making choices about which parts of humanity's farthest messenger get to keep functioning and which have to shut down forever. Voyager's power comes from radioisotope thermoelectric generators, essentially nuclear batteries that convert heat from decaying plutonium-238 into electricity. At launch in 1977, Voyager 1's RTGs produced about 470 watts. That's roughly the power consumption of a decent gaming computer. Nearly 50 years later, as the plutonium continues its inexorable radioactive decay, power output has dropped to around 220 watts. And it keeps falling, losing approximately 4 watts every year. 4 watts doesn't sound significant until you realize what it means in practice. That's enough power to run a small LED bulb. Every year, the equivalent of 1 bulb's worth of electricity vanishes from the spacecraft's available budget. Engineers have to decide what gets sacrificed to keep critical systems alive. The first casualties were the heaters. Starting around 2019, engineers began shutting down heaters that kept various components within their tested temperature ranges. The scientific instruments were supposed to operate within specific thermal limits. Going below those limits risked permanent damage or erratic behavior, but keeping the heaters running meant less power for everything else. So they made a calculated gamble: shut off the heaters and hope the instruments could handle the cold. They could. Temperatures dropped well below design specifications. Some instruments now operate at temperatures they were never tested at during ground development, but they keep working. Why? Nobody knows for certain. Maybe the original thermal requirements were overly conservative. Maybe the vacuum of space provides better insulation than expected. Maybe it's just luck. This pattern has repeated across multiple systems. Engineers identify something that seems non-essential. They calculate the power savings. They transmit the shutdown command and wait 2 days to see if the spacecraft survives. Usually it does. Sometimes they discover surprising consequences that force them to rethink their assumptions about how systems interact. The attitude control thrusters present a particularly delicate challenge. Voyager uses small thrusters to maintain its orientation, keeping its antenna pointed precisely at Earth. As power declines, running these thrusters becomes progressively more expensive in terms of available electrical budget. But without proper orientation, the spacecraft can't communicate. It's a fundamental requirement that can't be compromised. In 2017, engineers faced a thruster crisis. The primary attitude control thrusters had been firing continuously since 1980, nearly 40 years of operation. They were showing signs of degradation, requiring more heat and power to produce the same thrust. If this trend continued, they'd eventually fail completely. The solution was audacious. Voyager has backup thrusters that hadn't been used since the Saturn encounter in 1980. These trajectory correction maneuver thrusters were designed for a completely different purpose, making large course adjustments during planetary flybys. But they could theoretically handle attitude control if configured correctly. The problem? Nobody knew if they'd still work after 37 years of dormancy. The fuel lines might be clogged, the valves might be frozen, the heaters might have failed. And if the test went wrong, Voyager could tumble out of control, losing communication forever. They did it anyway. On November 28, 2017, engineers sent commands to fire the backup thrusters for the first time in nearly 4 decades. Then they waited the standard 45 hours for confirmation. When the data came back, the thrusters had fired perfectly. They switched over completely, buying potentially years of additional operational life. This episode reveals something crucial about managing Voyager. Every decision carries enormous risk because there's no possibility of physical repair. You can't send a technician, you can't install replacement parts, you can't even directly observe what's happening. You send commands into the void and hope they work. The power budget also affects how much data Voyager can transmit. Lower power means weaker signals. Weaker signals require longer integration times at the receiving antennas to extract usable data. Longer integration times mean lower data rates. Lower data rates mean less science gets transmitted back to Earth. Currently, Voyager transmits data at roughly 160 bits per second. That's slower than the earliest dial-up modems from the 1970s. At this rate, sending a single smartphone photo would take hours. But it's sufficient for the spacecraft's current mission, measuring the plasma, magnetic fields, and particles in interstellar space. These measurements don't require high bandwidth. They're simple readings that compress into small data packets. Still, engineers constantly juggle priorities. Should they allocate power to the plasma wave instrument or the magnetometer? Should they collect more frequent measurements or extend the mission duration by reducing sampling rates? Every choice involves trade-offs between scientific return and operational longevity. The science team has a wish list of measurements they'd love to make if power were unlimited. They'd run all instruments simultaneously at maximum sensitivity. They'd sample more frequently to catch transient phenomena. They'd transmit redundant data for error checking. But power limitations force brutal prioritization. What's the single most important measurement right now? That's what gets power. This creates an interesting dynamic, where Voyager's mission has evolved from intensive planetary observation to sparse interstellar monitoring. During the Jupiter and Saturn flybys, instruments ran continuously, cameras snapped photos every few seconds, and data poured back to Earth at the maximum rate the spacecraft could manage. Now, decades later, instruments cycle on and off in carefully orchestrated sequences designed to maximize scientific value while minimizing power consumption. The October 2024 incident that triggered the fault protection system illustrates how fragile this balance has become. Something caused an unexpected power draw, possibly a cosmic ray hit, possibly a component briefly malfunctioning. The fault protection system detected the anomaly and automatically switched to lower power backup systems to prevent total failure. This autonomy is crucial. With 2-day communication delays, Voyager must be able to protect itself when things go wrong. The onboard fault protection monitors power levels, temperatures, and system status. If parameters exceed safe limits, it takes defensive action without waiting for instructions from Earth. It might shut down non-essential systems, It might switch to backup hardware. It might reduce data transmission rates to conserve power. These autonomous responses save the mission. But they also complicate operations because engineers discover problems only after the spacecraft has already reacted. They received telemetry showing that Voyager switched to the S-band transmitter 3 days ago. Now they have to figure out why, determine if it's safe to switch back, and craft commands to restore normal operations, all while working through that 45-hour communication lag. The S-band transmitter incident is worth examining in detail. This backup transmitter operates at a lower frequency than the primary X-band transmitter. Lower frequency means the signal can penetrate through various obstacles better, but it also means the signal is even weaker when it reaches Earth. About 1/5 the strength of the X-band signal. When Voyager switched to S-band in October 2024, engineers at the Deep Space Network faced a detection problem. The S-band signal was so faint that standard reception techniques barely registered it. They had to use specialized signal processing, longer integration times, and creative filtering to extract the spacecraft's message from the cosmic background noise. The fact that they succeeded demonstrates the extraordinary sensitivity of the Deep Space Network antennas. These dishes can detect signals carrying less power than a single snowflake hitting the ground. They're listening for whispers from across the solar system, pulling coherent data from electromagnetic noise that's billions of times stronger than the signal itself. But even the most sensitive antennas have limits. As Voyager's power continues declining, its signal will keep getting weaker. Eventually, probably sometime in the 2030s, the signal will drop below the detection threshold. The spacecraft will still be functioning, still collecting data, still transmitting. But Earth won't be able to hear it anymore. That inevitable silence creates a strange situation. Voyager won't die in any dramatic way. It'll just fade beyond our ability to communicate with it. The spacecraft will continue operating on its remaining power, executing whatever final commands were uploaded until the RTGs decay below the minimum voltage required to run any systems at all. Even then, Voyager won't stop existing. It'll just become inert, a silent artifact tumbling through interstellar space, carrying its golden record with greetings in 55 languages, music from across human cultures, and images showing what Earth and its inhabitants look like. Current projections suggest that by 2036, there won't be enough power to operate even a single scientific instrument. By that point, engineers might be able to receive basic engineering telemetry, enough to know the spacecraft is still alive, but not enough to collect science data. A few years after that, there won't be enough power to run the transmitter at all. These projections assume steady decay and no catastrophic failures. But Voyager has already exceeded expectations so thoroughly that making confident predictions feels presumptuous. Components that should have failed years ago keep working. Systems operating outside their design parameters continue functioning. The spacecraft demonstrates a resilience that its designers probably hoped for, but couldn't guarantee. This resilience comes partly from over-engineering, building systems with safety margins that could accommodate decades of degradation. But it also comes from something harder to quantify. The original engineers made thousands of small decisions about component selection, circuit design, and system architecture. Many of those decisions were guided by intuition and experience rather than formal requirements. They chose parts that felt robust. They added redundancy where it seemed prudent. They designed systems to fail gracefully rather than catastrophically. Those accumulated choices created a spacecraft that could survive 47 years in space. Not because anyone explicitly designed it to last that long, the mission was supposed to end after 5 years, but because the foundational engineering philosophy emphasized durability over cutting-edge performance. Modern spacecraft design often goes the other way. Engineers optimize for capability, accepting reduced reliability to achieve higher performance. They use state-of-the-art components that offer incredible functionality, but might not survive decades of operation. They minimize mass and power consumption, which means less margin for degradation. This approach makes sense for missions with defined timelines. If your spacecraft only needs to function for 5 years, designing it to survive 50 is wasteful. You're carrying extra mass that reduces your scientific payload. You're using outdated components when newer technology could provide better results. You're spending money on redundancy you'll probably never need. But Voyager's extended lifetime demonstrates the value of that conservative approach. The mission has returned science for 47 years because the spacecraft was built to withstand anything space could throw at it. And it's still working. The Deep Space Network handles that eventual silence in a way that's both practical and melancholic. As Voyager's signal weakens, DSN engineers will gradually allocate more antenna time to the spacecraft, shifting from shared observation windows to dedicated tracking sessions. They'll combine signals from multiple antennas to boost reception sensitivity. They'll adjust data rates downward, trading information quantity for signal reliability. But there's a hard limit to what even the most sensitive receivers can detect. Radio signals obey inverse square law. They weaken proportionally to the square of the distance. Double the distance, and you need 4 times the antenna sensitivity to maintain the same signal quality. At Voyager's current distance, the signal arriving at Earth carries less power than it takes to illuminate a single pixel on a digital watch display. As that distance continues growing, the signal will eventually drop below what's called the noise floor, the background electromagnetic hiss that permeates space. When that happens, no amount of antenna combining or signal processing will recover Voyager's transmissions. The information will still be there, encoded in radio waves spreading outward from the spacecraft. But it'll be buried so deep in background noise that extracting it becomes mathematically impossible. Engineers know roughly when this threshold will arrive. Current projections suggest that by 2036, Voyager won't have enough power to operate scientific instruments. A few years later, it might manage basic engineering telemetry, simple status reports indicating the spacecraft is still functioning. Then, probably by the late 2030s or early 2040s, the transmitter will shut down entirely. These projections carry significant uncertainty. They assume steady degradation and no catastrophic failures. They assume the RTGs continue producing power at predicted rates. They assume no major component breakdowns beyond what engineers can work around remotely. Any of those assumptions could prove wrong. What engineers can't predict is whether Voyager will experience a sudden, catastrophic failure that ends the mission abruptly, or whether it'll gradually fade as systems shut down one by one. The spacecraft has already demonstrated remarkable resilience through decades of operation in conditions that weren't fully understood when it launched. Components have survived temperature extremes, radiation doses, and mechanical stresses that exceeded their design specifications. That resilience comes partly from the conservative engineering approach used in the 1970s. Designers selected components with large safety margins. They included redundant systems wherever mass budgets allowed. They chose proven technology over cutting-edge capabilities. This philosophy created a spacecraft that could absorb decades of degradation while continuing to function, but it also comes from luck. The specific trajectory Voyager followed, the particular radiation environment it encountered, the thermal cycling it experienced, all of these factors affected component reliability in ways that couldn't be fully predicted. A slightly different path might have exposed critical systems to radiation levels that would have caused failures years ago, or it might have avoided radiation altogether, allowing the spacecraft to operate even longer than current projections suggest. The November 2023 computer failure demonstrates both aspects of Voyager's situation. The failure itself, a single memory chip in the flight data subsystem, represented the kind of gradual degradation that engineers expected would eventually affect the spacecraft. After 46 years of continuous operation in the harsh space environment, it's surprising that more components haven't failed. But the nature of the failure also revealed how much margin remained in the system. Engineers could work around the failed chip by relocating code to other memory locations. They could delete obsolete routines designed for planetary encounters that ended decades ago. They could optimize and compress the remaining code to fit within the available space. The spacecraft had enough functional resources left to absorb this failure and continue operating. That repair process itself showcased the extraordinary capabilities of the deep space network. When Voyager sent back that initial corrupted signal in November 2023, that repeating pattern of ones and zeros, DSN engineers had to decode a transmission format they'd never seen before. The spacecraft was trying to communicate, but not in its normal language. One DSN engineer spent hours analyzing the signal pattern, comparing it against documentation of the FDS architecture, looking for recognizable structures in what appeared to be random noise. Eventually, they identified it as a memory dump, a complete readout of the FDS memory, transmitted in a format that bypassed the normal data packaging routines. This kind of detective work requires both deep technical knowledge and creative problem solving. The engineer needed to understand 1970s computer architecture, data formatting conventions from that era, and how the FDS organized its memory. They also needed to recognize that the gibberish signal might actually contain structured information encoded in an unexpected way. Once decoded, that memory dump became the key to diagnosing the failure. By comparing the actual memory contents against how the system should be structured, engineers could identify exactly which section of memory had failed and what code resided there. This allowed them to develop the repair strategy, relocating that code to other memory locations. Implementing that repair required another set of challenges. Engineers had to divide the affected code into sections small enough to fit in available memory spaces scattered throughout the FDS. They had to modify each section so it could function in its new location. They had to update all references to that code elsewhere in the system. And they had to do all of this using documentation from the 1970s, much of it on yellowed paper or old mimeographs. Several of the original Voyager engineers had retired or passed away. The current team was essentially archaeological detectives, piecing together design decisions made nearly 50 years ago by people who never imagined the spacecraft would still be operating in 2024. Why did they structure the memory this way? Why did they choose this particular data format? What assumptions were they making about how the system would be used? These questions mattered because any modification had to respect the original architecture. The engineers couldn't simply rewrite the FDS software from scratch. They were working with a system that had been optimized for 1970s hardware constraints and couldn't be fundamentally restructured. They had to work within the framework the original designers created, making minimal changes that preserved the system's overall logic. The repair process took 5 months from when the failure first occurred in November 2023 to when science operations fully resumed in June 2024. During that time, Voyager was essentially in a coma, alive but unable to communicate meaningful information. Engineers sent commands and waited 2 days for responses, trying different diagnostic approaches, analyzing the results, formulating new hypotheses. When the fix finally worked on April 20th, 2024, the relief at JPL was palpable. For the first time in 5 months, they could see the spacecraft's health status. They could verify that all systems were functioning normally. They could confirm that no other problems had developed during the months of troubleshooting. But that was just the first phase. Engineering telemetry was flowing again, but the scientific instruments remained silent. Over the following weeks, engineers repeated the repair process for the code that handled science data. They relocated those routines to new memory locations, tested them, and gradually brought the instruments back online. By June, all 4 science instruments were operational again. The magnetometer resumed measuring the interstellar magnetic field. The plasma wave instrument continued detecting electron oscillations in the surrounding plasma. The cosmic ray detector went back to counting high-energy particles. The low-energy charged particle instrument returned to monitoring the distribution of ions and electrons. This repair demonstrated something remarkable about the human capacity to solve problems across vast distances and timescales. The spacecraft is more than 15 billion miles away. Signals take 45 hours for a round trip. The computer system being repaired was designed half a century ago, using technology that's now obsolete. The original engineers are mostly gone. The documentation is fragmentary and aging. Yet despite all these obstacles, engineers managed to diagnose a complex computer failure, develop a repair strategy, implement it successfully, and restore full functionality. They did it using patience, creativity, and deep technical knowledge. They did it by thinking through the original designer's logic and finding ways to work within constraints that would seem impossibly restrictive to modern software engineers. The success of this repair raises questions about how long engineers can continue solving Voyager's problems remotely. Each failure removes some margin from the system. Each workaround uses resources that can't be replaced. The spacecraft is gradually consuming its own redundancy, converting backup capabilities into primary systems to compensate for components that fail. Eventually, a failure will occur that can't be worked around. Maybe it'll be another memory chip in a location where code can't be relocated. Maybe it'll be a critical component in the transmitter or receiver that prevents communication entirely. Maybe it'll be a power system failure that shuts down multiple systems simultaneously. When that happens, The mission will effectively end, even if the spacecraft continues functioning. Without communication, there's no way to receive data or send new commands. Voyager will execute whatever final instructions were uploaded and then continue operating autonomously until its power supply decays below minimum operating levels. The team knows this is coming. They're already planning for it, deciding which final commands to send, which systems to prioritize in the remaining operational years, how to maximize the scientific return from whatever time remains. They're documenting everything about the spacecraft's current state, so that future generations might understand what happened after communication ceased. Because even after contact ends, Voyager will continue existing. It'll keep traveling outward at 38,000 miles per hour, adding another billion miles to its distance every 7 years. In about 40,000 years, it'll make its closest approach to another star, passing within about 1.5 light-years of Gliese 445 in the constellation Camelopardalis. By then, Voyager will be a completely inert artifact. No power, no active systems, just a metal structure carrying its golden record, still moving through the void. The spacecraft will continue that journey for billions of years, long after Earth itself has changed beyond recognition, carrying humanity's message to whatever might eventually find it. The Deep Space Network isn't just impressive because of its antenna size. It's the sensitivity that matters. These dishes can detect signals arriving with less power than what's needed to run a digital watch, a billionth of a watt. That's what Voyager's signal delivers when it reaches Earth, a whisper so faint it barely exists above the cosmic background noise. 3 complexes form the network: Goldstone in California's Mojave Desert, Madrid in the mountains northwest of Spain's capital, Canberra in Australia's outback. They're positioned roughly 120 degrees apart in longitude, which means as Earth rotates and one complex loses sight of Voyager below the horizon, another is already bringing it into view. Continuous coverage, 24 hours a day. Every single day, each complex operates multiple antennas. The largest dishes measure 70 meters across. That's 230 feet of precisely curved metal surface. These massive structures can tilt and rotate to track spacecraft across the sky with extraordinary precision. They're so sensitive that they can detect the thermal radiation from distant planets, measure the wobble in a spacecraft's trajectory caused by gravitational anomalies, and pick out Voyager's feeble signal from trillions of miles away. When that strange garbled signal came back from Voyager in March, after the poke command, it wasn't in the expected format. The spacecraft was trying to communicate something, but the message was scrambled. An engineer at the Deep Space Network decoded it anyway, pulling meaning from chaos through technical expertise and creative interpretation. That decoded signal contained the complete memory readout that revealed the failed chip. Without the Deep Space Network, this repair would have been impossible. You need that sensitivity to hear the spacecraft. You need that global coverage to maintain constant contact. You need that technical expertise to interpret unexpected signals. The network is humanity's lifeline to its most distant explorers. But here's what makes this even more challenging. Voyager's distance keeps increasing. Every second, it travels another 11 miles farther from Earth. Every day, another million miles. Every year, another 360 million miles. The signal gets weaker. The round-trip communication time gets longer. In November 2026, Voyager will reach 1 light day from Earth. That's the distance light travels in 24 hours, roughly 16 billion miles. At that point, if an engineer sends a command on Monday morning, the response won't arrive until Wednesday morning. 2 full days for a round trip. Every diagnostic test, every repair attempt, every software patch, all requiring minimum 48-hour cycles. This creates a fundamental constraint on how the mission operates. You can't troubleshoot in real time. You can't try something, see if it works, and immediately adjust your approach. Every decision requires careful planning. Every command needs thorough testing and review before transmission. A mistake could make things worse or permanently disable the spacecraft. The October incident demonstrated this perfectly. On October 16th, Voyager experienced another problem. 3 days later, it fell completely silent. The team suspected the fault protection system had triggered again, switching off the main X-band transmitter to conserve power. But which backup system had it switched to? The spacecraft hadn't used its S-band transmitter since 1981, over 40 years ago. That transmitter operates at much lower frequency than the X-band, which means the signal is even fainter when it reaches Earth. Finding that signal was like searching for a candle flame from across an entire continent. But the Deep Space Network found it anyway. Engineers reactivated the X-band transmitter and resumed normal operations by early November. Crisis averted. But each incident consumes resources. Each workaround reduces future options. The spacecraft is gradually using up its redundancy, converting backup systems into primary systems to compensate for failures. Power is the ultimate limiting factor. Voyager's radioisotope thermoelectric generators convert heat from decaying plutonium-238 into electricity. When the spacecraft launched in 1977, those generators produced 470 watts. Nearly 50 years later, the output has declined dramatically. The spacecraft loses about 4 watts every year as the plutonium continues decaying. 4 watts doesn't sound like much, but when your total available power keeps shrinking, every watt becomes precious. Engineers have been managing this decline for decades, making careful decisions about which systems to keep running and which to shut down. About 5 years ago, they began turning off heaters for some science instruments. The instruments were designed to operate within specific temperature ranges, and letting them get colder meant risking permanent damage. But the team had no choice. They needed to conserve power for critical systems. Surprisingly, all the instruments continued functioning despite reaching temperatures far below their tested limits. The hardware proved more resilient than its specifications suggested. Earlier this year, the team had to shut down a science instrument on Voyager 2 to conserve power. Each shutdown is a loss, data that will never be collected, measurements that will never be made. But it's necessary to extend the mission's operational lifetime. Current estimates suggest the spacecraft might maintain enough power to return engineering data until 2036. Science operations will end sooner, probably by the early 2030s, when there won't be enough power to run even one instrument. After that, Voyager will still exist, still function, but it won't be able to tell us what it's experiencing. The spacecraft has surprised engineers before. Systems have operated at temperatures well below their rated limits. Components have lasted decades beyond their design life. The entire mission has exceeded every expectation. But physics imposes hard limits. Radioactive decay follows an inexorable curve. Eventually, the power output will drop below the minimum needed to maintain communication. When that happens, the mission effectively ends, even if the spacecraft remains functional. Without power for the transmitter, there's no way to receive data. Without power for the receiver, there's no way to send new commands. Voyager will execute whatever final instructions were uploaded and then continue operating autonomously until its systems shut down one by one. The team is already planning for this. They're deciding which final commands to send, which systems to prioritize, how to maximize scientific return from the remaining operational time. They're documenting everything about the spacecraft's current state, creating a detailed record for future generations who might want to understand what happened after communication ceased. This isn't the first time Voyager has faced serious technical problems. In May 2022, the attitude articulation and control system started sending nonsensical data. Engineers fixed it by routing the telemetry through a different computer. In December 2023, the flight data system failed, leading to the 5-month repair effort. Both Voyagers lost portions of their memory during the Prime mission decades ago, and they've experienced numerous unexplained anomalies over the years. Each problem required creative solutions tailored to the specific failure and the spacecraft's limitations. The fact that engineers have repeatedly found workarounds speaks to both the robust original design and the ingenuity of the support teams. But it also reveals something about the nature of these repairs. They're not fixing the underlying problems, they're working around them, using redundant systems, relocating code, routing signals through alternate paths. Every workaround consumes some resource that can't be replaced. Every repair uses up margin. The spacecraft is gradually depleting its own resilience, converting backup capabilities into primary functions to compensate for failures. Eventually, a failure will occur that has no workaround. Maybe it'll be another memory chip in a location where code can't be relocated. Maybe it'll be a critical transmitter component that prevents all communication. Maybe it'll be multiple simultaneous failures that overwhelm the engineer's ability to respond. The increasing distance makes every future repair more difficult. As Voyager moves farther away, the round-trip communication time grows longer. Diagnostic cycles take more time. Testing solutions requires more patience. The engineering team must think even more carefully before sending each command. In some ways, maintaining Voyager is like caring for an aging patient with a chronic condition. You manage symptoms, you work around limitations, you make difficult triage decisions about which functions to preserve and which to let go. You know that eventually, despite your best efforts, the decline will continue until something critical fails. But unlike a patient, Voyager won't simply cease to exist when communication ends. The spacecraft will continue its journey, a silent traveler moving through interstellar space at 38,000 miles per hour. It'll keep adding distance, keep moving away from the solar system, keep carrying humanity's message encoded on its golden record. In about 40,000 years, Voyager will make its closest approach to another star, passing within roughly 1.5 light-years of Gliese 445 in the constellation Camelopardalis. By then, the spacecraft will be completely inert. No power, no active systems, just a metal structure with gold-plated records attached, still moving through the void at the same velocity it has now. The spacecraft will continue that journey for billions of years. long after Earth's continents have shifted beyond recognition, long after the sun has exhausted its hydrogen and begun swelling into a red giant, long after human civilization has either spread to the stars or vanished entirely. Voyager will still be out there, a testament to what humans achieved in the late 20th century. That's the strange duality of this mission. In one sense, it's ending soon. Power is declining. Systems are failing. Communication will cease within a decade or two. But in another sense, the mission is just beginning its longest phase, an eternal journey through interstellar space that will outlast everything that created it. The engineers managing Voyager understand this. They know their work has a finite timeline. They know that someday soon, probably within their own careers, they'll send the last command and receive the last signal. After that, Voyager will be beyond human reach, an autonomous artifact carrying our message to whatever might eventually find it. Until then, they'll keep monitoring every signal, analyzing every data packet, watching the slow decline of power and the gradual failure of systems. They'll make the choices that need to be made, which instruments to shut down, which heaters to turn off, which redundant systems to sacrifice to keep essential functions running just a little longer. The relationship between these engineers and Voyager has become something more than technical stewardship. It's personal in a way that's difficult to articulate. They're maintaining humanity's connection to a spacecraft that's becoming less and less like a machine and more like an ambassador, a representative of our species, carrying a message that might outlast our civilization by billions of years. That message, the golden record attached to each Voyager, contains sounds and images selected to portray the diversity of life and culture on Earth, music from different cultures and eras, greetings in 55 languages, sounds of wind and rain, birds and whales, a mother's kiss and a beating heart, images of humans, animals, landscapes, architecture and scientific diagrams. The record was designed to be playable by any technologically advanced civilization that might encounter it. Instructions for playing it are etched on the cover in what scientists hoped would be a universal language, physics and mathematics, the hydrogen atom's characteristic wavelength, binary notation, pulsar locations to identify our solar system's position in the galaxy. Carl Sagan and his team spent months selecting the contents, debating what would best represent humanity to an alien intelligence. What music captures the essence of human creativity? What images convey who we are? What message should we send to beings we might never meet? The golden record transforms Voyager from a scientific instrument into something more profound, a time capsule and message in a bottle combined. Even if every system fails, even if the spacecraft becomes completely inert, it'll still carry that record, still represent us to whatever might find it. And the odds of anything finding it are vanishingly small. Space is incomprehensibly vast. Voyager's path doesn't take it particularly close to any known stars for tens of thousands of years. By the time it approaches another stellar system, that system's planets will have moved. The chance of any civilization detecting and retrieving this small, silent object drifting through the void is almost zero. But almost zero isn't zero. And that infinitesimal possibility gives the mission a significance that transcends its scientific achievements. Voyager represents humanity's first attempt to send something beyond our solar system that might survive long enough to be found by another intelligence. The engineers maintaining Voyager understand this dual nature of their work. On one level, they're troubleshooting a failing spacecraft, relocating code, managing power budgets, working around broken systems. On another level, they're preserving humanity's connection to our most distant creation for as long as physics allows. Each successful repair buys more time. Not just for science, though. The data Voyager continues to collect about interstellar space remains valuable. But time for humanity to maintain that connection, to know that something we built is out there, still functioning, still exploring, still representing us in the cosmic void. The 2024 repair was particularly significant because it demonstrated that even with decades-old technology, with systems operating far beyond their design specifications, with components failing in unpredictable ways, human ingenuity could still find solutions. The engineers took a spacecraft with 68 kilobytes of memory, less than a single modern text message, and performed the equivalent of brain surgery across 15 billion miles using 45-hour communication delays. They did this by understanding not just how the systems work, but how the original designers thought. By reading yellowed documents and faded mimeographs, by reconstructing the logic and intentions of engineers who built these systems before personal computers existed, before the internet, before most of the modern world. That connection across generations, current engineers channeling the thinking of designers from the 1970s, mirrors the larger connection Voyager represents. A link between different eras of humanity, different levels of technology, different perspectives on our place in the universe. When Voyager launched in 1977, the Cold War was at its peak. The world seemed divided into permanent ideological blocks. The idea that humanity might speak with one voice to the cosmos seemed almost naive. Yet the Golden Record attempted exactly that, to represent Earth as a unified whole rather than a collection of competing nations. Nearly 50 years later, the world has changed in ways the Voyager team couldn't have predicted. The Soviet Union no longer exists. The internet has connected humanity in unprecedented ways, while simultaneously revealing new divisions. Climate change has emerged as an existential threat. Private companies are launching rockets that would have seemed like science fiction in 1977. But Voyager keeps going. Its trajectory determined decades ago. Its message unchanged. Its function as humanity's representative, unaffected by political shifts or technological revolutions or cultural changes. That persistence carries its own message. The spacecraft demonstrates that some human achievements transcend the moment of their creation. That engineering excellence and scientific curiosity can produce something that outlasts its creators and their entire civilization. The engineers know their time with Voyager is limited. They can see the power curves declining. They can project when critical systems will fail. They know roughly when communication will become impossible, probably within the next decade, almost certainly before 2036. But they also know they're part of something larger than maintaining a spacecraft. They're extending humanity's presence in the cosmos for as long as possible. They're ensuring that when Voyager finally falls silent, it'll be because physics made continued operation impossible, not because human error or insufficient effort allowed preventable failures. The October 2024 communication hiccup, when Voyager switched to its backup S-band transmitter, demonstrated both the spacecraft's autonomous resilience and the increasing fragility of the mission. The fault protection system worked exactly as designed, protecting critical systems by switching to lower power mode without waiting for instructions from Earth. But it also showed how thin the margins have become. The Deep Space Network had to detect an extremely weak signal using a transmitter that hadn't been used since 1981. If they hadn't found that signal, if the S-band had failed, or if the DSN couldn't detect it, the spacecraft might have been lost permanently despite still functioning. These close calls will become more frequent. Each system operates closer to its failure point. Each repair consumes more margin. Each workaround uses up resources that can't be replaced. The engineers prepare for each scenario they can imagine. They develop contingency plans. They identify which systems can be sacrificed and in what order. They map out the sequence of graceful degradation that'll extend operations as long as possible. But they also know that eventually, something will happen they can't fix. Some failure will occur that has no workaround. Some combination of problems will overwhelm their ability to respond, or the power will simply decline to the point where no configuration can maintain communication. When that day comes, they'll send a final command. Maybe it'll be instructions for the spacecraft to continue collecting data, even though it can't transmit anymore. Information stored in memory that no one will ever retrieve, but collected anyway, because that's what Voyager does. Maybe it'll be a final systems check. Maybe just an acknowledgement that this is the end of communication. And then Voyager will be on its own, truly alone in a way it hasn't been since launch. No more commands from Earth, no more course corrections, no more repairs or workarounds or careful management of declining resources. Just a silent traveler moving through interstellar space at 38,000 miles per hour, carrying its golden message to whatever might eventually find it. The spacecraft will continue adding distance for billions of years. It'll pass through regions of space humans haven't named and will never see. It'll witness cosmic events, supernovas, stellar collisions, planetary formations that no human instrument will ever detect. It'll outlast not just the engineers who maintain it and the scientists who built it, but the entire species that created it. That's the strange mathematics of interstellar travel. The mission's operational phase, the part where humans control and communicate with Voyager, represents less than 1/1,000,000% of the spacecraft's total journey. The vast majority of Voyager's existence will be spent silent and autonomous, long after humanity is gone. The engineers understand this. They know they're managing the brief opening chapter of a story that'll continue for billions of years. They know the real mission, carrying humanity's message through the galaxy, has barely begun and will continue long after they're gone. So they keep working, keep troubleshooting, keep finding solutions to problems that seemed unsolvable. Keep extending operations one more day, one more month, one more year. Not because they believe Voyager will run forever, but because every additional day of operation is a gift. Every new piece of data from interstellar space is valuable. Every moment of continued communication is precious. And when the final signal comes, when Voyager sends its last data packet and falls permanently silent, they'll know they did everything possible. That they extended humanity's reach into the cosmos as far as physics and engineering would allow. That they gave Voyager every possible chance to complete its mission. The spacecraft will continue its journey regardless, moving through the void at the same speed, carrying the same message, representing humanity to the cosmos, whether we're there to monitor its progress or not. That journey is Voyager's true mission, not the data it collects or the systems it operates, but the simple fact of its existence as humanity's first attempt to touch the stars. That's the real legacy of the April 2024 repair. Not that engineers fixed a computer from 15 billion miles away, though that achievement stands on its own. The legacy is what that repair represents about human persistence in the face of impossible odds. Think about what actually happened. A single memory chip failed in a computer built in the 1970s. That chip contained code critical to the spacecraft's ability to communicate. The engineers couldn't see the failure directly, couldn't touch the hardware, couldn't run standard diagnostics. Every command they sent took 45 hours for a round-trip response. They had to work with documentation from nearly 50 years ago, yellowed papers and fading mimeographs written by people who never imagined the spacecraft would still be operating in 2024. Many of those original engineers had retired or died. The current team was essentially doing archaeology, reconstructing the thinking of designers from a different era, and they succeeded. They decoded a garbled signal that turned out to be a complete memory dump. They identified the exact chip that had failed. They devised a solution that required splitting code into sections and distributing those sections across different memory locations. They modified each section to work in its new home. They updated every reference throughout the system. Then they transmitted the fix and waited 2 days to see if it worked. When the response came back on April 20th, 2024, Voyager was talking again after 5 months of silence. But here's what makes this story different from typical engineering achievements. This wasn't about building something new or pushing technology to its limits. This was about keeping something alive that should have died decades ago. About refusing to give up on a machine that's already exceeded every reasonable expectation. Voyager was designed for a 5-year mission. It's been operating for 47 years. It's traveled farther than any human-made object in history. It's sent back data from realms no other instrument can reach. And it's still working. That continued operation isn't luck. It's the result of thousands of decisions made by hundreds of people over nearly 5 decades. Engineers who built in redundancy they didn't strictly need. Scientists who chose robust components over cutting-edge performance. Mission planners who prepared for contingencies they couldn't fully predict. And now, decades later, engineers who spend their careers maintaining a spacecraft that's older than most of them are, who pore over documentation from before they were born, who develop creative solutions to problems that shouldn't be solvable with 1970s technology. Each repair buys a little more time. Each workaround extends operations a few more months or years. But the ultimate outcome is inevitable. Power continues declining. Systems continue failing. Distance continues increasing. Eventually, communication will end. Current projections suggest science operations will cease by the early 2030s. Engineering telemetry might continue until 2036 or so. Then silence. Not because the spacecraft stops working, but because it won't have enough power to run its transmitter. When that day comes, Voyager will execute whatever final commands were uploaded and continue operating autonomously. It'll keep collecting data that no one will receive, keep following its programming until the power supply decays below minimum operating levels. Then it'll become completely inert, a silent artifact tumbling through interstellar space. But even then, the mission continues, because Voyager's ultimate purpose isn't collecting data or testing systems or demonstrating technology. It's carrying humanity's message to whatever might eventually find it. The golden record attached to the spacecraft contains sounds and images from Earth, music from different cultures, greetings in 55 languages, pictures of humans and animals and landscapes, instructions for playing the record etched on its cover in what scientists hoped would be a universal language of physics and mathematics. That record transforms Voyager from a scientific instrument into something more profound, an ambassador, a time capsule, a message in a bottle thrown into the cosmic ocean. The odds of anything finding it are vanishingly small. Space is incomprehensibly vast. Voyager's trajectory doesn't take it particularly close to any known stars for tens of thousands of years. By the time it approaches another stellar system, the planets will have moved. The chance of detection is almost zero, but almost zero isn't zero, and that infinitesimal possibility gives the mission significance that transcends its scientific achievements. Voyager represents humanity's first attempt to send something beyond our solar system that might survive long enough to be found by another intelligence. In about 40,000 years, Voyager will pass within 1.5 light years of Gliese 445. By then, the spacecraft will be completely dead. No power, no active systems, just metal and silicon and gold, still moving through the void at 38,000 miles per hour. It'll continue that journey for billions of years, long after the engineers who maintain it are gone, long after everyone alive today is forgotten, long after human civilization has either spread to the stars or vanished entirely. The spacecraft will outlast the continents, outlast the oceans, probably outlast the Earth itself. When the sun swells into a red giant 5 billion years from now and consumes the inner planets, Voyager will still be out there, moving through interstellar space, carrying its golden message. That's the strange mathematics of this mission. The operational phase, the part where humans control and communicate with Voyager, represents less than 1/1,000,000% of the spacecraft's total existence. Everything we've done, all the planetary encounters and scientific discoveries and engineering repairs, all of it is just the opening moments of a story that will continue for billions of years. The vast majority of Voyager's journey will happen in silence. After we lose contact, after the spacecraft becomes inert, after humanity is gone. Just a piece of 1970s technology drifting through the galaxy, outlasting its creators by eons. The engineers who repaired Voyager in 2024 understand this. They know their work extends something that's already lasted far longer than anyone expected. They know communication will end soon, probably within their own careers. They know the real mission, the one that will continue for billions of years, has barely begun. So they keep working, keep troubleshooting, keep finding solutions to problems that seemed impossible. Not because they believe Voyager will run forever, but because every additional day of operation is valuable. Every new measurement from interstellar space matters. Every moment of continued communication is precious. When the final signal comes, when Voyager sends its last data packet and falls permanently silent, they'll know they did everything possible, that they extended humanity's reach as far as physics and engineering would allow. that they gave Voyager every chance to complete its mission, and the spacecraft will continue its journey regardless, moving at the same speed, carrying the same message, representing humanity to the cosmos, whether we're there to monitor it or not. That's what the 2024 repair really accomplished. Not just fixing a computer or restoring communication or enabling continued science operations, though those achievements matter. What it accomplished was extending our connection to humanity's most distant ambassador for a little while longer, keeping alive, for a few more years, our link to something that will eventually become the longest-lasting testament to human civilization. Because long after everything else we've built has crumbled to dust, long after our cities and monuments and records have vanished, Voyager will still be out there, still carrying its golden message, still representing us to the universe. A spacecraft repaired from 15 billion miles away, kept alive by engineers who refuse to give up, carrying humanity's message to the stars. That's not just an engineering achievement, that's something else entirely. Something that touches on what it means to be human. Our curiosity, our persistence, our need to reach beyond ourselves into the unknown. Voyager will keep going. And someday, billions of years from now, something might find it, might decode the golden record, might learn that once, on a small planet orbiting an ordinary star, there existed a species that built this machine and sent it into the darkness, that looked up at the stars and wondered, that refused to accept the boundaries of their world. That's the real message Voyager carries. Not the sounds or images on the golden record, but the simple fact of its existence. That we were here, that we tried, that we reached as far as we could into the cosmos, knowing we'd never see the end of the journey. The engineers who maintain Voyager aren't just keeping a spacecraft alive. They're extending humanity's presence in the universe for as long as physics allows. And when they finally send that last command, when Voyager falls silent and begins its eternal autonomous journey, they'll have succeeded in something remarkable. They'll have kept our most distant ambassador talking for nearly 50 years. They'll have extracted every possible moment of operation from a machine that should have died decades ago. They'll have demonstrated that human ingenuity can solve problems across billions of miles and half a century of technological change. And Voyager will continue, silent but still moving, inert but still carrying our message. A testament to what humans achieved in the late 20th century, traveling through the galaxy long after we're gone. 15 billion miles away, and getting farther every second, still working, still exploring, still representing us to whatever lies beyond.